So we're going to talk about a bit of a hobby project, but if we're pretty broad, this is a talk about many problems, if you will. Because there are moments when we know a solution to a problem well enough that we can compare solutions. We can say this solution to the problem is better than this solution of the problem, but it might not be the same that we can say this is the best one that it'll ever be. This is a talk about these sorts of problems, and these problems include problems like the traveling salesman problem. We have to try to figure out a route that goes via all the cities. Very often, if you want to get an optimal flight schedule in, that's also kind of a big problem. Many scheduling problems are. Problems like optimal packing problems also fall into this category. And even things like getting robots to walk tends to, the lovely bit where the robots keep falling. But these are sort of very hard problems in general, and you want to do something about it. Now, the reason that these problems typically are hard is because they're easy to score, but very hard to optimize. So it's super easy to say, hey, let's try out this one solution, and what's the score that belongs to it? What's super hard is to say, take all the possible solutions, go over all of them, and just pick the best one. It's so hard, in fact, that academia to find a set of acronyms to describe how hard these problems are, and they usually start with the letters N and P. This means that usually, instead of worrying about optimality, we try to worry about finding a good solution in a limited amount of time. So let's say within a day, here's a problem, we kind of want to have a solution that performs well enough. So we're in a different country. And to solve these sorts of problems, you'd usually resort to heuristics to search for like the giant search space. Very often they involve creating a set of possible solutions. And typically you do things to these solutions like random changes. You try to do like a greedy improvement. You try to remove a bad candidate. And you try to generate as many good candidates. But it's always kind of a wishy-washy mix and match of the steps you do like this. And all of these steps can be done in a similar way, but there's something very general going on here. So let's say I'm trying to find an optimal solution to a traveling salesman problem. You kind of see that depicted here. I have a couple of tours that I start out with, and let's say then I pick the best one, and then from that best one I say just copy that one, and then make like weird small changes, and then you have a new population. This is one version of such an algorithm, but if you maybe switch it around just a little bit, so you say, hey, maybe I have a different way of mutating, and I have a slightly different way of filtering, this is a completely different algorithm in a way, but it's also a very similar algorithm in a way. And there's maybe a level of abstraction that if we can maybe make a library for some of the common steps, we might be able to make it easier to make problems solvable for that are very specific. So we started this library called Evol that makes it easy to define an evolution of heuristic search steps that you can apply to a population. It kind of feels like working on a data frame in Spark, but instead of data, we are dealing with a population of solution candidates. We'll evolve this population over many iterations, and the goal of this talk is to demonstrate this library and to show some things we've learned and some advice. We will now quickly go over some key parts of the API before we're going to dive into examples.
Yeah, thanks. So, first of all, I have to say, so the idea of this library is not to make a library that is extremely quick in solving problems and that will solve every problem that exists in the world. The idea is that you can, using this library, you can make a problem solver extremely quickly. Just try things out that's just easy to put some basic ideas together and just have a lot of fun. It's probably, since it's in Python, it's not going to be the fast algorithm you write anyway. So anything, whenever you do anything with an evolutionary algorithm, the first thing that comes to mind is that first you have a population. So that's the most common noun you'll ever see in an evolutionary algorithm. In Evol, you will first make a population that consists of individuals. And so there's two ways to do that. Either you just make a list of individuals and you put that and you instantiate the population with that together with a cost function, or you have the population generate the individuals using an initialization function. So using this population, you can then use some verbs. So first of all, probably the most important step is you're going to filter. And so we haven't called that filter, but we call this survive. So you have part of your population that survives. So first of all, underwater here, all the individuals are evaluated, and then some fraction, the most fittest candidates survive. So you can either specify a fraction, say 10%, or a fixed absolute number, say 10. And then after doing that, you're probably going to want to make new solutions, new individuals. So that's breed. So after survive comes breed. And for breed, you need a parent picker. You need some function that determines who are going to be the parents of your new individual. So for example, here I have an example function that's really the simplest case you can imagine. It's pick random. It just takes the whole population, takes one random parent, one parent. And then you need a combiner function, which combines all the parents together into a new individual. In this case, that's really simple. You take the parent and you copy it. You're done. Okay, so then we have survive, breed, and then of course the last step is mutate. In this case, you just take the individual, take the chromosome of the individual, and you mutate it a little bit. So maybe depending on chance, maybe, I don't know. It's up to you. You define this mutator function. In this case, it's flip bits, so given you have a list of bits, you can flip it. So these methods of the population, they are chainable. And the nice thing about chainable methods is that you can chain them. Which means that you can just, in one statement, take your population, mutate them, then have half of them survive, and then breed new ones so that your population has the same size as initially. And so, well, of course, this is just one step in an evolutionary algorithm. You want to probably do this 100 times, so you can do this 100 times. And, well, so come on, this is 5 lines and you have your evolutionary algorithm. Of course, you need to define all the functions first, but we cannot do that for you because that really depends on the problem you're solving. But there's a better way. So what you can also do is you can define an evolution instead. So the evolution is an object that sort of has the same verbs. You can call mutate and survive and breed on it. And all it does, it just makes a sort of prescription of what the algorithm should do with the population. So once you've defined this evolution, you can apply it to your population by calling population.evolve my evolution 100 times. Or the other way around, you can say evolution, just evolve this population. And this is really nice if you have, for example, 2 patterns that you want to follow. So first you have one evolution, evolution 1, and then you have number 2, and first you want to do number 1 100 times and then number 2 50 times. And then you can mix this and match this as much as you want. I think it's time for an example.
Seems like it. So this example is going to be a little bit stupid, but it's going to drive the point home and how you would use such an algorithm. Let's say I'm playing something like blackjack, and the idea is the bank has a couple of cards and the player has a couple of cards. Certain cards are worth a certain amount of points, and the whole goal of the game is to get as close to 21 as possible. If you ever have a score that's higher than 21, your score gets to 0. So there's a bit of risk in getting a high score. The decision that you have to make is, given the cards that your opponent has and the cards that you have to say, do I want to grab another card from the deck? When you do this, you are risking that you're going to get a 0 because you might go over 21. The data structure that we then use to describe this is basically to say, okay, so there's a dictionary that has tuples as keys, and the first index of the tuple is going to say what's the score of my opponent. The second tuple is going to say what's my first card. The third tuple is going to say what's my second card. And basically, for every one of those game states that you could have, we have to say, are we going to draw a new card, yes or no? So that's a 0 or a 1. And you can imagine this is kind of a long dictionary with lots of tuples in it. And this algorithm has to decide, hey, what is the optimal strategy that we can have for this game? It's a bit of a silly example, but it has 1s and 0s, which makes it kind of nice. And again, the whole point of the game is you want to get a score that's higher than the bank, but you don't want to go over 21, because if you go over 21, then you're in deep trouble, then you get a score of 0. Now, the way that you would implement this is relatively simple. So I have this one function called simulate, where I can say, take that actions dictionary, pass that in, and then with the number of simulations that you have, simulate a game outcome against a random player. And we will do this for a population many and many and many times. I will have a population of 40 individuals. The first step of my evolution is to say, remove everyone except for the 5 best ones. Then pick 2, in this case, pick 3 random characters. I have a combiner function that just says, for every single action that is possible, just pick the one that the most parents have. That's sort of the most popular thing to do. And then mutate it, maybe flip a few bits at random, and do this over and over and over and over again. Then you learn something. This thing will run, and what you can then do is this, you can sort of log the population object, and you can get a nice visualization out. What you see on the left-hand side here is the population fitness over time, and what you see on the right-hand side is the data structure for the chromosomes. So every key is mapped to something on the x-axis, and if it's a 1 or a 0, it's either yellow or black, and you can see over time what the best chromosome is doing. And what you can see here is we're not learning anything. Currently, my genetic algorithm is failing, it's not picking up any patterns. And the reason is I'm not simulating enough. If you do the same thing, but you do it for 10,000 simulations, then boom, suddenly it learns something, and I see that my algorithm is performing better over time. The reason here, of course, is if the chromosome, of all the actions you can have, if, let's say there's 4,000 actions you could take, if you're only simulating 1,000 of those, then obviously you're not sampling the entire choice space. Small lesson we learned. This is just an example of something you could do with a genetic algorithm. But the thing I want to stress at this stage is it's not just a genetic algorithm that you can implement with this library this way. We just give you a couple of base verbs for you to play with. But if you want, you can also do simulated annealing or pheromone methods. Simulated annealing is kind of like saying we're going to mutate the population constantly. And as you can see here, so some of the members of the population get better, green, some of them get worse, red. And in the beginning of the iterations, we're fine if some of the population members get worse. However, as we sample more and more, a variable that we call temperature gets higher, and then we get more picky, which means that if someone gets worse, we don't sample the worst person, we just say you're going to stay exactly the same as you are. This is a variant of a heuristic, but you can imagine that might work. And this is something you can as well implement. You can also do something like a pheromone method. Basically, you generate a new population every single time, but the way that you generate a new population is dependent on the best ones of the current population. Basically, here, for example, you can say, hey, sort my entire population, take the better ones, get some sort of probability distribution from those, and then sample from that probability distribution to make a new population, and repeat this over and over again. Now, because it's the end of the day, I won't stress you with the actual code that does this, but the gist of it will look something like this. You just say, hey, there's something called a temperature that I keep track of, and at every single iteration, the temperature changes, and my mutation function will use that temperature to mutate my population. And the same thing you can do with the pheromones as well. The idea here is we're going to give you a small little framework that shows a direct line of thought that'll give structure to the way you're building your heuristics. This is one example, but our library has a bit more features if you want to do something in the order of learning how to play certain board games or card games.
So here comes another example, which is completely useless. Who of you does not know the game of rock, paper, scissors? Good. Well, then you know that unless you can predict your opponent's moves, there is definitely no winning strategy. I mean, it's completely random. So the goal of this example is not to make a good bot. I mean, there's plenty of websites where you can actually play against other people's bots. I'm not really interested in that. I'm just going to have a little bit of fun here. But first, you have to note that when we do this, we have a problem because we cannot define an evaluation function of a single chromosome. Because a chromosome is going to make a decision, either rock or paper or scissors, but that doesn't translate to a score. We cannot calculate a score of that. We need to have it compete against another player. And only then can it win or can it lose. That means so a chromosome on itself does not have a score, but it only has a score compared to another chromosome. And for this we have a solution. So instead of the normal population object, you use a contest population. And this just takes two more arguments. And one is the contests per round. So basically that means the number of contests every individual is going to play every time it is evaluated, and the number of individuals per contest. So for rock, paper, scissors, clearly that is 2, but of course it could be 100. And then the main difference here lies in how the evaluation function works. So the evaluation function here is going to look like this. It's not going to accept a single chromosome, it's going to accept 2 chromosomes, 2 players. And both of these players are going to make a choice. And then, well, we're going to return not 1 score, but 2 scores. So if they make the same choice, obviously it's a tie, so both of them get 0. And otherwise it completely depends on what they chose. and one of them gets +1 and the other one gets -1. And then over all these iterations, all the chromosomes play random games against other chromosomes, and we just sum the scores. And the ones that won the most games are the best ones. So for this, we still need to define a chromosome. In this case, it's not just a list or something. I made a class. It's a rock, paper, scissors player. And I made this one really, really stupid. The idea here is that, well, you can see, so when I initialize it, it sets a preference. So this player has a preference for one of the 3 options. And whenever you play, so depending on the arbitrariness, it's either likely to either pick a random choice or take its preference. So it's just a little more likely, up to very much more likely, to take the preference over a random one. Of course, that's a really stupid thing to do if you're really playing this against someone, because they'll find out if you have a preference. Well, again, we need an evolution. It just looks the same like always. And then, well, then it's the question, which is best? Is it rock, is it paper, or is it scissors? What do you think? Is this actually going to converge? Well, let's see. So here we go with the default settings. Here you see over the iterations, I did 200 iterations, and then you see the preferences of most of the population. And you can see that this varies, this fluctuates a bit. It does not converge, it just keeps fluctuating. But each of the preferences keeps about like 1/3 of the population. So no, it's not converging. But we can play around with this a bit more. For example, if we reduce the arbitrariness, so by default it was 1/2. If we set it to 1/4, which means that at least in 3/4 of the times the players are going to choose their preference, you see some interesting pattern emerge. It looks like it's oscillating. We can reduce the arbitrariness even more, to 10% or to 0. And then we just see oscillations. So what's happening here? Well, of course, your fitness here depends on the rest of the population. If you choose rock and all the others have scissors, then of course you're going to win. So then the next round, it's better to have rock. And the number of rocks is going to grow. And then it's better to be paper. If we also, if we reduce the fraction of individuals that survive each round, then we can even change the frequency of these oscillations. And this just, well, every round, it's completely, the odds are completely turned, and so the rules of the game have changed entirely. Like I said, it's useless, but I think it's fun.
So we started making this because partially we had a small joke. So this year at PyData Amsterdam, Rogier did a talk on risk analysis to get all the financial clerks into the room. But basically it was a bot that played the board game Risk. We thought it was pretty funny too. The idea behind this basically came from, we want to have bots that play board games and card games on our behalf. And that's kind of where this came from. But we ended up making something that might be a little bit more general. Making all this stuff, though, we did learn a couple of things. If you're building an algorithm, like if you do with a meta heuristic, whatever you do, even if you use our library, try to solve it on pen and paper first. Make sure you understand the problem very well. For all the crossover functions that you make and for all the mutate functions that you make, you have a function that can generate an individual, then you also have a function that can take an individual and mutate it, so you can write tests for these functions as well. Test everything and then pass it through. Understand your problem, much better than your solution, please. Otherwise, you get weird things that happen. Try to never, ever generate a candidate that is surely suboptimal. Sometimes you have people that say, oh, we need more randomness, we need more noise, we need to generate plenty of people to make sure that we don't get stuck. That's all very much true. But if you're sampling individuals that you know are going to be bad, you're going to be in bad territory. And mainly, try to think when you've exhausted hyperparameters, because something else might be going wrong. Having said this in general, though, our library, once again, is meant to make it more fun to play with heuristics and to give structures to these heuristics. It helps you to structure a heuristic search, but it may also well be the case that meta-heuristic methods are suboptimal. There are specialized solvers for certain problems out there that we will never beat. So if you know SciPy, there's a couple of optimization tools there. Google has open sourced operational research tools. So if you have traveling salesman's problems, Google OR tools actually has algorithms for this that you can just use from the box. that will always outperform anything you make here. Having said that, I do want to talk a bit about some of the features that we have. Because we are writing this in Python 3, we can make use of some dynamic typing. So in the function method I should say, we can actually say what sort of type of object we expect that goes into the method, but also the type of object that goes out. And you can do this with a string even. So you can see an evolution object goes into the evolution thing, and what goes out of this function is a population object. The nice thing about this is that if you're method chaining in a tool like PyCharm, you can autocomplete indefinitely. So you can make a chain that's like 10 long, and we will always be able to generate these autocomplete messages for you in PyCharm. Jupyter Notebook kind of does this, but not so much. But definitely if you're making this in PyCharm, you're making a command line app that optimizes this, this is a bliss to work with. We are going to be adding a couple of extra features to this. We love playing with this, but you can already download and play with this, but there's a couple of things that are still missing. If you run a genetic algorithm or any heuristic ever, you do want to keep track of the best solution you've ever had. And we want to solve that problem by offering a logging framework as well. That also makes visualization of the algorithm very easy. The idea basically is you just set where is the log file, and if that's ever set, we will make sure everything's logged appropriately. We should also be able to parallelize some parts. As I said before, some of these evaluations can be expensive. If I have to simulate a game 10,000 times because otherwise I won't converge, then that does mean that if I do a certain mutate and the mutate doesn't change the chromosome, I don't want to reevaluate it twice. We have a mechanic for that, but also when we're evaluating the scores, we can do that in parallel, because basically these are things that you can just apply a function to. So that's something we're going to add. We're also going to add a couple of nice helper functions, so how to select parents, how to maybe memoize some things. We're going to add support for that. And we are likely to be adding support for island populations. We just had a content population, which is a certain type of population that makes it useful to simulate certain types of problems. Island populations are populations where you can basically say, hey, there's a population, now split it up into 3 separate groups, and everything that's going to be happening afterwards is going to happen to every one of these groups independently. So if you do a breed or a filter, it happens per island, not on the entire population. We're also in the market for an informative logo that features humor. So if you know anyone who does illustration well, we're happy to learn more about that. Now, because we're getting at the end of the conference, though, we should talk about one last problem that we think is the funniest thing of this talk.
Yes, one last problem. I realize that I am right now, I'm in between you and your beer. Let's talk about that. So this is my first time in Warsaw, same for Vincent. So of course we need to explore the city. So what could we do tonight? How do we optimize this? Well, of course we need to visit some pubs. Which ones? Well, you can just look that up. Best 10 bars in Warsaw. Looks fine, right? Okay. So scrolling through this page, then we have to decide which pub to visit. Or better, in what order do we visit all these pubs? Okay, so let's get to it. How do we solve this? For starters, we need to navigate from pub to pub. So we need some information from Google Maps. So import Google Maps. Initialize the client, put in the addresses. Of course, we need to start at the conference right here. So that's the Copernicus Science Center. Google gets that. I don't need to type in an address. And of course, I like to end up at my hotel tonight, because otherwise I have to sleep in some bar. Now, okay, let's get the locations of these bars. So just call the API, geocode address, and then we can look up the locations which include latitude and longitude. We can also ask for walking directions, so we know exactly what the distance is between all of these pubs. And since it's only 10 or 12 things, we can just easily ask all the walking times or walking distances between all of the combinations. So using these latitude and longitudes, we can visualize it. These are all the pubs, including our hotel and the conference location, that we want to visit. Okay, good. Now again, we have to define a chromosome, which in this case is just the list of the pubs in the order, excluding the conference and the hotel, of course, because these are fixed at the ends. Combiner, just put 2 lists together. We use some crossover method. I'm not going to go into that. And some mutation, as in just flip to the location of 2 pubs in the list. And then, again, we need to define an evolution, which is just the same as always. Then we need a cost function, right? And the cost function is just easy, it's the distance. But there's something in here. As you visit more pubs, I'm pretty sure you're going to walk more slowly. And since these are 10 pubs, I think this is a significant effect. So we've included this with this drunk factor that increases with the number of pubs visited. I hope it's accurate. We still have to do some field testing. Okay, so then the results. We started a conference, and then, well, I'm sorry, I can't pronounce that, I think. But, well, here's the list, so you know where to go. Take a picture, but I'm afraid you'll have to substitute your own hotel at the end.
Your mileage may vary. It's also kind of.
So, again, visualizing this, this is what the solution looks like. It looks like it's found the optimal solution, right? Okay, so, but let's visualize it a bit more. I think this is more intuitive. So we start here at the Science Center. We cross the river. There's one pub there, and then we just go through all the old town, and then at the end, the red bar, the red pin, that's our hotel. So, ready to go? But unfortunately, so when I was actually doing this, I hadn't realized there would be an after party. So I guess we'll have to do this some other time. Thanks for listening. The code of... Of course, the code of Evol can be found on GitHub.
Let's do one question. Oh,
You do realize this question's between this and beer, right?
Okay, this one is short. Do you already brand it as a map reproduce algorithm?
Right. So no.
Okay, so
I think the first thing we're going to add is the just standard Python multicore, and keep it at that for a bit. This will never be the fastest way to do genetic algorithms. It just unlikely. If you really want to do it fast, maybe try it in Scala. It's not too hard to do this with the RDD API, I guess, but no. No.
okay, one more.
Hi. The oscillation observation that you guys saw, is it something you were expecting or something that took you guys by surprise?
So the first time I saw this...
You have to use the mic.
The first time I saw it, it took me a little bit by surprise. And then, of course, I went looking to get it like, well, first why, but of course, well, the moment you see it, it's sort of obvious because you can see that one population just eats the other up. But then, then I just went looking for it. How can I amplify this, and how to tweak this to make it as strong as oscillation as possible?
One small thing to add with this, we also have another colleague who did this for Monopoly. And there you kind of see the exact same thing. Because certain strategies beat other strategies, which get beaten by another strategy, which again gets beaten by the former strategy. So this is something, especially in board games and card games, you see all the time. Beer o'clock.
Beer.
Beer o'clock. Yeah.
A question. Okay. There's one more.
Okay, fine. Yeah.
I don't leave you.
It's actually more of a comment. I just wanted to say that you can't spell traveling salesman without ales.
Oh man, that's like a joke I should have put in the slides. Oh, it is. Thanks. Yeah, we're going to totally steal that.
Okay, I think this is a good point to finish today.